This is AS2 paper from January 08, and the topic of question 2 here is refraction. A ray of light in air strikes the surface of a medium of refractive index n at an angle of incidence I. Write down the equation relating n, I and the angle of refraction r. So this is our standard equation for refractive index. Snell's law, n equals sine of I over sine of r. Very straightforward. Part 2. State the two conditions which must apply if a ray of light incident on the boundary between two media is to be totally internally reflected. Well, firstly, the ray of light must be incident from the more dense medium. So it must be incident from the more dense medium. In other words, when total internal reflection is to occur, it must be coming from, example, from the glass towards the air. So we're coming from the glass-air boundary, not the other way around. And the second condition is that the angle of incidence within the glass block or water or so on must be greater than the critical angle. So two conditions: must be incident from the more dense medium, and the angle of incidence must be greater than the critical angle. Figure 2.1 shows a prism made of glass of refractive index 1.52. Each of the angles of the prism is 60 degrees, as shown in the diagram. A ray of light strikes face AB at point P at an angle of incidence of 45 degrees. After refraction at P, the ray crosses the prism to Q, where it is refracted out of the prism. So we have refractive index of 1.52, the question tells us, and the rest of the information is on the diagram. 60 degrees at each corner of the prism, and the incident ray is coming into face AB at point P at 45 degrees. We're now asked to calculate the angle of refraction R, which again is marked on our diagram, of the ray after it enters the prism at R. We're going to use Snell's law, which we wrote at the top, n equals sine I over sine R. So we can rearrange that as R equals the inverse sine of sine I over n. Now if you're not happy with this type of rearranging in algebra form, substitute in at this stage and then rearrange. But using the one I've already rearranged here, the incident angle was 45, the refractive index was 1.52, and that gives us an answer, or an angle, of 27.7 degrees. So again, I've used Snell's law, I've rearranged it in algebra form, that's an n, and substituted at that point to find an angle of refraction of 27.7 degrees. Two things to watch out for here. Make sure your calculator is in degrees. Perhaps if you've been doing other calculations, you may have your calculator set in radians, so you do need to make sure that it's set in degrees. And watch for this rearranging, that you use the inverse sign correctly. If you have any doubt about the rearranging in algebra, they say substitute into the original equation, work it out and rearrange. One other thing, when you work out the sine of an angle, don't ever write that value on your page because you're introducing a rounding error. Simply keep it on your calculator, divide it by the 1.52 and then inverse sine it. Moving on then to part 2. The refracted ray crosses the prism, striking face AC at Q. Calculate the angle of incidence, I, of this ray on face AC. And it's giving you a hint here. It's telling you that angle R plus angle I is equal to the angle of the prism. Let's look at the diagram again to see what we're looking for. We're trying to find this angle in here, I. And the question is telling us that R plus A is equal to the angle of the prism, so R plus A is equal to 60. So let's write that down first of all. R plus A is equal to 60 degrees. Well, previously we worked out that R was 27.7, so A is 60 minus the 27.7 degrees, which gives you 32.2 degrees. Now, if you had made an error in your calculation of A in the previous part, but used it correctly here, you would still gain your marks. Okay, part 3 then. In A part 2, you stated 2 conditions for total internal reflection. Show that one of these conditions is not satisfied when the ray meets face AC, so that the ray does emerge from the prism. Show you're working out clearly. Well, we know that A here is 32.2 degrees. It is travelling from the more dense medium towards the air, therefore it's not the first condition that we're thinking about. We have to think about that second condition. We have to try to prove that the angle of incidence must be greater than the critical angle for total internal reflection. So we want to show that TIR does not occur, so we want to show that A is less than the critical angle. So far we don't know the critical angle, but we do know an equation that will allow us to work it out. Sine of the critical angle is equal to 1 over the refractive index. So critical angle is equal to the inverse sine of 1 over n, which is the inverse sine of 1 over 1.52. That gives us a critical angle of 41.1 degrees when we work that out. So if A is 32.2 as we worked out, A is less than C, so no total internal reflection. You get 1 mark for that calculation and 1 mark for the answer with the comparison. Okay, then the final part. Calculate the angle theta to the normal at which the ray emerges from the prism. Let's just check the diagram again to find what we're looking for. Well, we know that the refractive angle in here is 27.7. We know that this angle of incidence is 32.2, and we want to find this theta emergent angle. As the ray is now leaving the glass and going to the air, we can say that 1 over n is equal to sine of A over sine of theta. To rearrange that, we then find theta is equal to the inverse sine of 1.52 times the sine of the A, which was 32.2 degrees. And when we work that out, theta is 54.1 rather. 54.1 degrees. You get a mark for that equation, using it correctly with 1 over the refractive index, because in this case we're going from glass to the air. And then 1 mark for your final answer. Okay, so to summarise in that question, we stated an equation linking the angle of incidence and refraction. That's actually Snell's law. We stated 2 conditions for total internal reflection. We then used Snell's law to calculate an angle of refraction and did a further calculation to find the angle of incidence on the glass to air boundary at the other side of the prism. And then we used our critical angle and refractive index to prove that the ray that meets that boundary is not totally internally reflected, but actually emerges as a refracted ray from the prism. And then we calculated the emergent angle using 1 over n equals sine I over the sine of the emergent angle. And we use 1 over the refractive index because in this case we're going from glass to air.